So now that you've seen some of the coolest elements of color guard, I'll tell you what it actually is, since that is definitely a common question. Color guard is a sport or activity where we spin and toss flags, rifles, and sabers. We accompany the marching band during halftime shows of football games to add a more visual element. Some history on color guard. It originated from military color guards that would carry flags, such as the American flag, banners, rifles, and sabers. They would travel with bands that played patriotic songs. Competitive drum and bugle corps sparked the beginning integration of modern color guard during the 1960s. At the University of Texas, the band director Vincent R. DiNino began using 4x6 silks, or the actual flag part, on wooden poles. They were handmade by his wife. Color guards quickly spread throughout the Southern Conference of Colleges and eventually to high schools around the country. Now, color guard is an activity at most high schools, colleges, and sometimes even middle schools. We no longer use wooden poles, though. We swap those out for metal poles ranging from 3 to 6 feet. And generally speaking, our silks are not handmade. Next, I have a preview of what I will discuss during this presentation. First is kinetic energy, then tangential velocity. Third, torque, and finally, time aloft. These will all relate to color guard in some way. First is kinetic energy. Here we have a problem that says, if after tossing a flag the velocity is 0.31 meters per second, and the mass of the flag is 0.91 kilograms, what is the kinetic energy of the flag? Let me dive into this topic with a more hands-on approach. As you can see, I'm applying force to the flag, which makes it have kinetic energy. This is because it is moving. So here I am drawing our little guy who's going to illustrate my different formulas. In this case, he will be tossing a flag up into the air. When he tosses the flag, there is kinetic energy. This is because kinetic energy is the energy of motion. It is also the amount of work the object can do because of its motion. We have mass in this problem, which is 0.91 kilograms, and velocity, which is 0.31 meters per second. Back to the earlier calculation, we have velocity, which is distance over time, and our mass of our flag. The final answer ends up being 0.0437 joules. Converted into calories, it's about 0.01, which is like eating some cucumbers because they contain less calories than the body uses to break them down. And they also help build muscle, like color guard. A more common example of kinetic energy is a roller coaster. At the bottom of the hill, it has the most kinetic energy because it has to move up the next hill. At the top of the hill, it had its most potential energy, and when it came down, all of that was converted into kinetic energy, therefore helping it to move. Next, I have a graph. When mass is doubled, the kinetic energy is also doubled, making the relationship between the two direct. So the more mass you have, the more kinetic energy you have. My next graph shows how if velocity is doubled, the kinetic energy would increase by a factor of 4. This is because velocity is squared and directly proportional to kinetic energy. So if you were to triple the velocity, the kinetic energy would increase by a factor of 9. Next is tangential speed. This is similar to velocity, but the direction of the motion is always tangent to the path of the object. This problem says, if you spin a flag 3 times, the time it takes is 7 seconds. The radius of the flag is 0.84 meters. Find the tangential speed of the flag. Here you can see it in action. A circle is being created, and the radius is from my hand to the end of the pole. So our little guy will spin the flag and create tangential speed. The formula for this is tangential speed equals 2 pi r over the period, which is the time for one circle. Our radius is 0.84 meters, and in this case we have 7 seconds for 3 spins. So our period will be 7 divided by 3, which is 2.3, and that is our time for one circle. So, back to the word problem from earlier, your final answer ends up being 2.3 meters per second. This is about 3 to 4 miles per hour, which is the speed of a walking turtle. My graph for this one shows how, if the time for one spin triples, the tangential speed decreases by a factor of 3, making time and speed inverse. This makes sense, because the more time spent spinning a flag for one rotation, the slower it is going to go. This next graph shows how if the radius is increased, tangential speed will also increase, making the relationship direct. This can be related to a bug on a rotating record. The bug on the outer edge of the record is traveling faster in order to complete the circumference in the same amount of time, even with its larger radius. The next subject is torque, which is a measure of force that causes an object to rotate. In this problem, the length of the lever arm is 0.3 meters, and the force is 8.92 newtons. Find the torque. Here I am demonstrating a toss. One hand pushes down, the other pulls up, and causes the flag to rotate completely so I can catch it correctly. Let's take a closer look. First, you'll select a point in the middle of the flag. From that point to your hand is length 1. From that point to your other hand is length 2. There will be an upward pulling force and a downward pushing force. So you have 2 torque calculations in the end. So you have torque equals force times length. So it's 8.92 newtons of force, and 0.3 meters is the length. In the end, you will get the total torque, which is torque 1 plus torque 2. The written calculation looks like this. The final answer ends up being 5.35 joules. Torque also happens when a wrench rotates around a nut or a bolt. That nut or bolt is the pivot point. In my graph for this problem, if the length of the lever arm is decreased by half, torque is also decreased by half, meaning that the length of the lever arm and torque are directly proportional. This can relate to someone pushing a door open towards the inside of the door. This reduces the length of the lever arm and makes the door harder to rotate around the hinge. Last but not least is time aloft. When a flag is shot across to a partner, an arc is formed and there is time aloft. If the vertical velocity is 5 meters per second, and assuming gravitational acceleration is 9.8 meters per second squared, then what is the time aloft? So here's a demonstration. When I toss the flag, it is lofty, and there's time aloft. The formula for this one is the absolute value of 2 times the vertical velocity divided by acceleration of gravity. The vertical velocity for this problem is 5 meters per second. Acceleration of gravity is 9.8 meters per second squared. To find the vertical velocity, divide the vertical distance over the time it took to reach the other partner. The full length calculation looks like this. The final answer ends up being 1.02 seconds. This is the time it takes for the sun to emit 3.8 times 10 to the 26 joules. Also, 2.4 babies are born. In a completely different arena, time aloft is created during pumpkin chunkin'. This is when pumpkins are shot out of cannons and they form arcs similar to the flag, although they travel much farther and are lofty for longer amounts of time. My last graph shows how, if velocity is doubled, the time aloft is also doubled, making the 2 variables directly proportional. In review, I have talked about how there is kinetic energy when a flag is tossed because it is moving. Also, when a flag is spun, a circle is created, meaning there is a circumference, which is 2 pi r. Using the period, we found the tangential speed of the flag. Then I discussed torque. When a flag is tossed, parts of the pole become lever arms, and there is an upward and downward force. These forces and lever arms create torque and cause the flag to rotate. Last was time aloft. I demonstrated how a partner toss created an arc in the air, and there's time aloft. Now that you've learned about the physics of color guard, you can appreciate the science and the beauty behind it.